will absolutely will be protected with the with the help of the carrier wave. So look back today, what we are going to take the today classes exactly. Let us take the MRAPSK. MRAPSK, I think probably I've explained in the last class, but still before going, I'll explain. Before going to that, let me have a look at the QPSK, what we call it as a quadrature phase shift QS, as exactly just going by the, what is exactly the quadrature phase shift key, I mentioned it. Okay, exactly. The quadrature phase shift key is the one, exactly what will happen. Quadrature phase shift key is, there's a one symbol, let us say one gimbal symbol, let us say the transmit message maybe one. This one symbol will be converted into what exactly? Two signal, S1 of 2, S2. This is for 1 and this is for 0. And this information will absolutely protect with what I call carrier wave cos omega ct, and another carrier, another symbol will be protected by this, and both together added, and the symbol will be represented. Symbol will be positive. This is exactly called quadrature. Because why we call it as a quadrature? Because the phase shift frequency which is used, phase shift frequency which is used in the carrier in order to protect the symbols for S1 of t and S2 of t or 90-degree difference together. That is why we call as quadrature phase shift, because each will have phase shift and by 90 degree, and we call it as a quadrature. In shortly, we call it as QPSK. So look back here. So we have what is exactly the equation. This is, as we know, signal of anything should be considered the magnitude of the energy and phase and frequency. The phase and frequency will identify through the what exactly the basis function, what we call phi. Okay, yeah, exactly. Any kind of energy, any kind of signal can be represented with the product of the energy of the, that is product of the energy, that is magnitude, that is information multiplied to the phase of that. So since QPSK takes the quadrature here, okay, exactly, that the cos of 2 pi ct into 2I minus pi by 4. Look back here. The possible value, even though quadrature is 90 degree, the possible value can taken by what you call S1 of 2 and S2 of 2 is equal to pi by 4, 3 pi by 4, 5 by 4, 7 pi 4. The quadrature difference, the difference between is exactly 90 degree. So this equation, what exactly S of will holds good for what a QPSK, square root of 2e by 2 into cos of 2 pi ct into 2I minus 1 pi by 4. Okay, exactly. So we derive this is all things. Look back, very important one point is here. Very looking for that point is exactly one symbol will have a 2 bits. And we look at one more very important point to be noted, because for one bit to be transmitted, 2 bits will be created. For each bit will have again 2 bits, what we call die bits. Okay, please remember, one of the information that is one to be transmitted, right, that is right, transmitted to the signal will be by converting the 2 bits. Then again 2 bits out of each bit of 2 bits will have 2 bits called the die bits, because the frequency of each, imagine cos omega ct, that is the carrier wave frequency absolutely used for S1 of t. In order to transmit one, will have a frequency integer plus or minus 5, plus or minus n psi b2. That means for one bit transmission, 2 bits will be transmitted. From each bit will have 2 bits. That is why we call it as die bits, one for positive value, another for negative values. So the possible value of such, we call possible set of phase values for Fc is equal to Nc by 2. Look back here, Fc is equal to Nc by 2 here. Okay, exactly. Nc by 2 is called as a gray coded set of die bit. For 2 bits of binary information, S1 of 2 is this much. Now, what is exactly the signals phase? Okay, exactly the signals phase of that signal phase is equal to indicate what exactly indicate the where the signal has to be present. Okay, exactly, signal has to be present, from which the receiver will identify where the receiver will identify the received information is is of the same of the what transmitted equation, or otherwise in words I can say, if the receiver will deduct the same bits as that of this. If it is sent 1, and then it'll deduct that whether the received information is 1 or 0 by looking what exactly signals phase, that is the representation of the signal will win that. Okay, so look back here, we have this two very clear. See, look back, this is the QPSK equation, The cos of expanding by this to yesterday expand a minus b, we'll get back to this equation. Look back here, there's a two terms, absolutely cos of 2 pi c by 2 into pi by 4. Similarly, sine into 2i minus pi by 4, this is this one. Okay, exactly, this is absolutely the signal, the energy of the signal into what exactly phases of the signal is this much. Okay, so look back here, this is the equation of the QPSK. QPSK will have two. One is for plus E into cos, one is for minus 2 into sine pi c. That means the information will have by leaving this. So we'll have a two message points. One message point for cos omega ct, that is for S1 of t, let us say S1 of t to represent the 1. Another one is for sine omega c, is it to represent the what bit of the zeros. That we have two message, e into or square root of e square root of e into cos this minus square root of e into sine omega ct. So when you look back, as I mentioned there, one bit will be 2 bits. For each bit, again 2 bits. That means what we that term we call as a gray codate. Okay, 1 1 0 1 0 0. These are the information. These are the phases. Absolute. We'll have these are the points. When you draw these all the points in a signal space from which that receiver will exactly deduct the information 1 and 0 of this. Okay, exactly. This is the signal point. When you look back to this, so how is this QPSK generation goes? The first, let us say this is the input signal to be transmitted. From whatever the input signal is there, it converts into what exactly there, what you call odd. This is one for odd, one for even. Look back, 0 1 0 0 for odd, 1 0. That means 0 bit of the information, 1 bit of the information, third bit of the information, fifth bit of the information. These exactly, okay, these bits. Okay, one is exactly called odd number of this thing. Second one is exactly what even number of this. Odd and even will be sum together will exactly what QPSK forms. Okay, right. So now how this generation goes, very simple. Binary input, and I mentioned in PSK we should have the polar NRZ level because the curve point, that is a very important. Please remember, in PSK we have to use the polar NRZ level, and this will be what exactly will be passed on to deduct the demultiplexer depending upon the message 1 or 0. If it is 1, that absolutely goes and multiplying into the what exactly the basis function which are, we give the information basis function which are generated locally by the transmitter and add together, we'll get back. Similarly 1, again phase value basis value multiplied together. When you come back to the coherent deductions, exactly this is exactly the coherent deduction here. The input is this is the received signal x of t. Each x of t will go to the one correlator. This is exactly we call it as a correlator. Each correlator will be multiplied with the different basis function which are generated locally, and it will be integrated by this fact. And decision device, exactly this is decision devices will check into the aspect. This is absolutely, this is what coherent deduction point which you mentioned it. And last class we had dealt with error probability is the one. How exactly the error probability of a QPSK is the one which gives the probability of detecting the received information by the receiver is false. That means if the transmitted message is 1, the receiving message is absolutely maybe zeros. So these are the equation where exactly we derive the probability error P dash is equal to Q by square root of E by N naught. Okay, this is we received, and we exactly find out bit error of the QPSK is given by this. And similarly, when you're talking about power spectrum, I told you the power spectrum of this, because look back, PSK uses only one carrier wave, which, see, very important in the QPSK, even though we use a two signal, one signal for transmitting the message 1, another signal for 1 0, but it uses only when the carrier frequency. The most of the information, the magnitude will be within this. Now let's go back MRA PSK, very important. MRA PSK, look back here, very important, especially when when we analyze these QPSK equations. That is, we have a two terms. One is exactly cos and sine. Okay, exactly. Just remember the point of the, just remember, when you remember that equation will be consist of what? One is the signal will be considered cos omega ct minus another energy of the signal into what? Sine omega. There is a phase difference is quadrature. Now, this quadrature, that means absolutely again the quadrature signal, that is called either sine and cosine. The cos for S1 of 2, which is represent the 1, at 0 the sine of omega ct passing for S of 2 to represent the what exactly 0. If this 2 bit will be different by 90 degree, we call it as QPSK. The phase between these two can take any different values. Let us say can different values. Okay, exactly. That means M values. So absolutely such kind of special case of QPSK we called as MRAPPSK. That is MRA what a phase shift key. That means instead of the quadrature, two signal. For one signal, you are going to transmit two bits, especially in the QPSK. Instead of that, what we are in 2 bits, the carrier wave which is used to protect that information, S1 of 2 and S2 of 2 in QPSK, the phase difference is 90 degree. But here what will happen? It may take M possible values that we call it as MPSK. What we need to change in the QPSK, this is the QPSK equation as you know, 2e by 2 into cos of 2 pi ct into 2, 2 minus 4. Instead of the 2 pi by 4, we can absolutely take it by what I call M. That is exactly M equation, which is here next. This is exactly the M equation, right? Where energy of the signal pursuing FC of this. So this is what we termed as, this equation we call it as MPSK. Everything is same. What the QPSK, how the QPSK generates S1 of 2, how the QPSK will be generated through QPSK transmitter, and how it will be did. Everything is same, but only thing is the difference is here, the phase difference between the S1 of 2 and S2 of 2, what we have seen in the PSK, which is 90 degree, but instead of here M or a PSK, it uses M possible values. That is why we change only the phase value of that, and it gives the M or a PSK. Okay, exactly. So when you come back to this, you look back, since S1 of SI of T, the signal M for a PSK can be of many signal with the different phases, because it can take M possible, no define. Therefore, M or a PSK can be extended. It has to be two terms, because when you take it to two equation, pi 1 and pi 2, because as you know that QPSK has to be two different signal will have a phase, and signal space, that is a representation of the signal which is used by the receiver in order to deduct the information is correct or wrong. That is exactly uses the base function. N is equal to two-dimensional Euclidean space is required, pi 1 and pi 2. Therefore signal MPSK is a two-dimensional in the Euclidean spaces which you mentioned here. So look back here, this is two functions. This signal space are M phi of 2 and phi of 1. Here absolutely what exactly, this is the point. Okay, this is phi 1 and phi 2. We have the messages M1, M2, M3, M4, M5 like this, which you have the messages here exactly. For exactly M is equal to 8, the M is equal to 8, message point is 8. Within this, we can point a circular symmetric, okay, circular message points are here, and the decision boundary between M1 and M2. See, this is what is the, see, look back, there is a gap from this. Whether this point, the influence of M1 up to this point, M1 up to this point. So we need to find what is the influence of N on either side of the M1. We call it as decision boundaries. Exactly, this is exactly called as a decision boundary. Okay, so look back here. Okay, exactly here. See this bus, and the distance between exactly here, the distance between the 2 point D12 and D18. So D18. Okay, exactly. This is the message one. Distance between the two. That is the distance absolutely in this. Okay, exactly. Okay. So this is absolute. This is absolutely D12 and D18. 2 square root of E into cos pi this distance of this, which is given by this. Okay. So when you took back this is, so that means what is the probability? Now let's talk about what is the probability of error by MRAPSK. That means we need to identify that deducting the information by MRAPSK is false. That means absolutely whether the received information is deducting by the receiver is 0, even though so the transmitted message is 1. Okay, such we call as probability error deduction. Here what will happen when you come back to the MRAPSK, we can think of the probability error of MPSK is just, it's the only difference with QPSK is we have a number of message points. Each will have a different possible values of phases instead of having what a quadrature phase difference as in QPSK. That means probability error of the QPSK multiplied with the number of distance between the each point absolutely gives probability error of symbol error of MPSK. That is why we call it as, look back, the probability error of QPSK is given by the QPSK is multiplied into the distance between the two messages here. So P is equal to Q by this. By rearranging, we have this equation. Exactly. So what is exactly the M spectra of M array? The M spectra is what I call it as, this is, as you know, power spectra, which is absolutely everything is same as QPSK. Only difference is what exactly. That means absolutely only different values M is goes. What exactly the phase, the M power spectra of that is a magnitude of the energy, that is a magnitude of the information signals to be passed, has to be what exactly within this, within the plus or minus of the what exactly carrier wave. The for different values of M, we have the different values of the spectral density which are shown here. And what is exactly the bit rate? Consider bit rate of this. See, this is absolutely before bit rating taking place. This is what is the magnitude of this is absolutely given by, that is x squared SBF 2 into log 2 base mn and squared TB into F. TB is equal to bit rate, which is given in the last equations. Okay. So this is exactly the bit rate. Bit rate is given in terms of the EB2 into EB log m. These are the derivative, which is not a derivation, it is simple for a mathematical purpose of that. Okay. So what is the bandwidth efficiency is given by log 2m by B bit rate of the M array PSK is 2B by log m. Okay, exactly. Now let's come back to the another loss of the PSK, what we call it as M array quadrature multiplication. Look back, very important here. M array quadrature multiplications. Look here, absolutely here. What is exactly the quadrature? Simple, I told you in the quadrature. As simple here, okay, what you call it as, okay, in quadrature, in QPSK, what we told that in the similar manner, in what we'll have, let us say two messages to be transferred, M1 of 2 and M2 of 2, two messages, each one will be multiplied. Let us say this is before sending. Let us assume that before sending, this has to be protected with the help of the what exactly the carrier wave. What is exactly the carrier wave? One more carrier wave will be generated local oscillator. This in low cos omega ct, okay, will protect this information. That means indirectly this M1 of 2 will put it across within this, that is analog signal, and we transmit. In a similar manner, what exactly M2 of another signal, that is another signal, will be multiplied with another carrier, which is of the 90-degree phase shift towards between this, okay, exactly, and multiply, and both will be sum together, and the information will be sent. As simple as QPSK. They have given us there's a quadrature, M array quadrature. Let me come back. Why this is, why it has to be different as with respect to QPSK and MPSK and M array. Why we are talking, because same technology has been same basic principle has been used in the QPSK. So look back, very important here is this. These are the two different signals. Where exactly in the QPSK one signal, for transmitting one signal, we generated two bits in order to deduct the information, or in order to enhance the bandwidth, which I talked to in the last class. Why this bandwidth enhancement, which I talked in the last class overs. Okay, here exactly here, instead of that one, instead of the 2 bits, you are going to send 2 signals. That means 2 bits you can send it at a time. Okay, that means you are going to utilize the channel bandwidth effectively. Please mind it, M array PSK, QPSK, all things for 1 bit, for one symbol, 2 bits will be generated for each bit. There is exactly what 2 bits, two bits of the 2 information, what we call as die bits, which I mentioned it, I shown to you in the last classes. Okay, exactly here, instead of that 2 symbol, 1 symbol, we are going to send 2 symbols. That is M1 of 2 and M2 of 2. That means 2 signal, 2 different information, not as a single symbol or a single information as in QPSK or MPSK. So 2 signals will be protected with a different what we call it as different phases, what we call it as quadrature amplitude modulation. Why? Because amplitude of the signal, the amplitude of the cause vary in accordance with this amplitude of the M1 of 2, and means with what exactly M1 of 2 will go into protect with this, and we are going to send it across to here. In a similar manner, another signal M2 of 2, which needs to be sent, will be multiplied to the sine omega ct. That means the quadrature phase difference, and this amplitude of this will be in very accordance with what exactly m2 of 2 will be summed together, will have what exactly q, what you call quadrature amplitude multiplication m1 of t into cos omega ct plus m2 of 2 into what exactly sine to omega t. This is exactly, we call this path, we call it as inverse path, and this path we call it as a quadrature path. From the basic principle of QAM, we can say that inverse and quadrature component are independent to each other, because they are independent. There is no doubt about, because this is one signal and this is a one signal. Only difference is the cost, just to make it, and okay, independent to each other, and they and exactly, and we can say, and the carrier waves amplitude in accordance with the information signal, that is m1 of 2 m2 with the different phases. Okay, that is m1 and m2 with the different. One is amplitude will be varied, and again the phases of these two will be also varied in accordance with that, we call it as. So look back here, along with the variation amplitude of the carrier wave, we can also vary the what phases of the carrier, because since we used m here, we are already using m amplitude here. Again, we are using m values. Each m value, the possibility of the phase. Okay, exactly. We call it as m or a quadrature amplitude multiplications. That is why we call it as quadrature. Where exactly? Please mind it, in MPSK and QPSK and MPSK or QPSK or BPSK, we only vary the phases. Where exactly M or a quadrature amplitude modulation uses both amplitude modulation and the phases. Imagine in the 2pm or a quadrature amplitude modulation, we have used two different signals, which are the two different symbols, where exactly MPSK or QPSK or BPSK used only one symbol to be transmitted with only varying the phases of the carrier. We never use the amplitude, where exactly M quadrature multiplication will give the option for both, absolutely for amplitude variation of each carrier wave along with the phases, and hence we call it as KM array quadrature multiplication. What is likely to be advantage we will likely to be get? I just mentioned it here. The bandwidth utilization is super big. For example, when we wanted to channel bandwidth as defined for certain frequencies f2 minus f1, we're going to send one signal for one symbol. Okay, here instead of that, we are going to send one signal which consists of two information. This is exactly one signal which consists of two signals which are in a phase difference, and hence we call it as quadrature amplitude multiplication. Two symbols will be represented, two signals will be represented within a one carrier wave and goes. Where exactly MPSK, QPSK, or all these things, we are going to send only one signal, only one with one signal with one symbol with the different phases for different symbols. Okay, absolutely. That is what this gives the advantage. That is why we can say array quadrature multiplication is give the option for both amplitude and the phase values changes, along with a very great advantages utilization of the bandwidth, because whatever we send the signal will be two information, the two information in one signal, that is this by Q of M of T. Will get back to what we call utilization bandwidth. It's absolutely perfect. If you say a bandwidth has been utilized, then that means that you are utilized with a higher frequency. What exactly it means dot or 8, because frequency indirectly, what is directly proportional to that time bat. Okay, so this is what the great advantage M or a QAM, which is absolutely used in today's communication system, because of course there are a kind of a disadvantage, absolutely, because DSP, this is double-sided bands. In the power spectrum, there is a double banded, kind of some disadvantage, but generally today's what we call telephonic industries or line communication systems uses this quadrature, because it gives like the bandwidth at higher level, and also it gives the higher frequency. So simply by understanding what is kind of the advantage of this, okay, what is exactly the equation? Absolutely nothing more here. This is for one equation. Look back here, very important, S1 of 2 QPSK. So same QPSK equation will be taken. What is QPSK equation? Energy of the magnitude of the signal into the phi phase will consist of the magnitude, will consist of the phase and frequency of the signal of a same bit, of a same frequency, very important, with the same energy. Okay, very important, please mind it here. So here in the QPSK, same energy of the signal, same phase, same frequency except phase. But in QPSK MRA, we are going to use different amplitudes, 2A, 2B, different amplitudes. That is AK and BK. Look back here, the coefficient which talks about different phases. That means this is one signal representation, this is another signal representation, and we have, see, that is what S1. This is what the equation is given by. The phase difference is absolutely given by this equation. This is a phase 1 is equal to this cos of 2 pi ct e into t minus cosine of 2 pi ct into t. The S of kt involves two phase quadrature which is modulated by sort of discrete amplitude. Okay, so what is exactly there's a signal space? Absolutely, signal space is very important, which is going to be used by the receiver at the coherent deduction. Okay, exactly whether the receiver is false in the region in order to predicate, in order to deduct that the information, the received information. We cannot use the predicate, we have to deduct. I'm sorry for that, but you can use it some little extent informally. I can say, you know, instead of predicate, you can use the deduct. The deduct of the information will be done by the receiver by using the signal space. The signal phase here is absolutely two. It consists of two basis function, phi 1 of 2 and phi 1 of 2 and phi 1 of 2, phi 1 of 2 and phi 1 of 1. One for first frequency, let us say cos omega ct. Another one will be for sin omega ct. These both function for both symbols in m array quam. So this is exactly d mean is equal to what? Distance between the concentrated message points in the signal space is depends upon the number of possible signals. Okay, simple aspect, nothing. So what is exactly L is equal to number of array in consolidation for every even number. So how many message? Because this is M array, the M means M possible of the phase. That means it takes a different message for a different points for M array. So lovely, let me talk about why this today data for why digital communication absolutely is the quite necessity for increase the high frequency. Simply I just mentioned in the last class, when you use M array, you will have a what we call it as a rate of transmission. Is that, for example, one positive pulse, within the positive pulse I can put three bits, that is a three symbol, that is an information. That means for one pulse I am sending for what exactly three pulse. Let us say that if there is a 3 bits, if there is a 3 bit, that is exactly 2 to the power of 3, 8 informations. That means within the 3 pulses, I can send 8 informations, and means that I am sending the information as very quick possible with a speed is directly proportional to time. Time is proportional to what exactly what we call the speed is indirectly proportional to time. Time is directly proportional to the frequency, and hence the rate of transmission is will be increased. Very important, you should mind it why the digital communication is so important. Apart from regular disadvantage, what we have mentioned, repetitive use, noise immunity, along with that, this kind of process very important point here. Okay, exactly. These are the signal space, and L is equal to number of array in a constellation for even number. L is equal to square root of m. L is equal to positive energy. Okay, exactly. So look back here, important. Mathematically, we can say that what we call we can use M array quam square constellation as Cartesian product of the two sets of the coordinator representing a pair of one-dimensional constellation is made up of set of all possible order of a bit. So there are this look back I have mentioned is that there are a lot of 8 points here, one point each, exactly each point of that. Okay, exactly each point of mathematically can use M array as a quant signal constellation as a product of the set of the coordination is made up of the set of all possible order pairs of a coordination with the first and coordinate. This is absolutely a very simple statement. This is okay. Just we are taken all the product just between this. See, look back. I mentioned in the last. This see product between these two, so what is exactly constellation within the square which is given by square root of m, and we have formulated. Let us not talk about because no derivations are just understanding purpose. Take the product and put it across to the what exactly because that is a possible message within the M array is possible. Okay, this is what there are a little extent of problems. Okay, and when little extent, I hope we can solve it in the coming classes. Okay, so this is what M array. Now let's go back. What is exactly a frequency shift keying techniques? That is one another method important. Okay, exactly ASK In ASK, we don't use much because amplitude varies in accordance, because on and off keys, we are not representing the zeros. So let us not talk about the ASK is not playing a very much role in the digital communication, because the information zero is also something. See, in binary, what exactly? Some information is there, zero. Zero is also some kind of information which were there, which has a negative pulse with a magnitude minus p. Where exactly in the amplitude shift key, we have missed the zeros. That means ASK is not a viable one in the digital communication, because zero is also some pulses. As for the binary sequence, each zero pulses will have some amplitude. Where exactly in ASK we transmit the message okay on off keying method. ASK is also called on for one wherever the symbol is one, where off for zeros. That means zero is off, means we cannot identify what is the magnitude of the zero pulses, that is minus EB or plus EB. So the plus EB, okay, fine, for one signal, zero is exactly will not transmit it, and it's quite bit difficult to identify the receiver, and hence ASK is not much, but PSK is absolutely very important role, and that is why we deal with the MPSK. That's why our syllabus talks about the today's concentration BPSK, what I call it QPSK, MPSK, and MPAM. You must understand these are very important fact. Now last very important one is exactly the frequency shift key. What is exactly the frequency shift key? See, let us say this is the information 10011 00001. This is has to be encoded in the line. Absolutely, please mind it. Here we are going to use of the what exactly the polar NR Z. Please mind, when you use the PSK, you must use polar NR Z. Okay. When you use FSK, you have to use polar NR Z equation here. Look back, this is the information to be passed. This is, look back, when you use some frequency, I use the frequency for transmitting one. Here, the transmitting one is a one frequency here, that is omega CT. When you're transmitting the what exactly, this will be have what exactly two. There is a two, what you call it as frequency, different frequency ones omega one. That means here by looking these two aspects, we can clearly say that the information to be sent, that is symbols, has been with a different frequency than for a zero, and it is another counter effect or a counterpart of the zero as the frequency for one. That means a different two frequency will be utilized. The frequency has been shifted depending upon the information to be passed, whether it's a one or zero. That's binary. We call it a frequency shift. Why is a frequency? They look by FSK. F stands for frequency. Frequency means changing the frequency required for transmitting. Shift the frequency level from one to other, and keying the one, we just put across to that information. We call it the frequency shift, shortly abbreviated as FSKs. Okay. So these are the FSKs. So now look back in the next class, we can do it. What is exactly the PSK, FSK? We'll do it. How the signal will be consist of, and how the current deductions is absolutely takes place. Okay, exactly how the current will be taken as BPSK and error probability of equation. Once you complete it tomorrow, probably I will complete the third unit by tomorrow. Tomorrow classes will be intimated by as early as possible. Thank you. Okay.